I am Karthik, Assistant Professor of Mathematics, SNS College of Engineering. In this lecture video, I will explain about conformal mapping in complex analysis. Introduction to conformal mapping. Conformal mapping is a powerful tool in complex analysis that deals with the transformation of geometric shapes in complex plane while preserving angles. Definition and properties of conformal mapping. Definition: a function f from the domain D in the complex plane to another domain D dash is conformal at a point Z if it preserves angles between intersecting curves at the point. In other words, if two curves intersect at Z in D, the images under f intersect at f of Z in D dash, and the angles between the curves at these points are the same. Properties. Angle preservation. The fundamental property of conformal mappings is that they preserve angles locally. Differentiability. Conformal mappings are typically functions that complex differentiable in their domain. Holomorphic functions. Conformal mappings are closely related to holomorphic functions. Local properties. Conformal mappings preserves not only angles but also other local geometric properties such as shape and size of small regions. Conformal invariance. Conformal mappings are invariant under conformal transformation. Analytic functions and conformal mapping. Analytic function. Definition of analytic function is: an analytic function, also known as holomorphic or complex differentiable function. It is a function f of z defined on a domain in the complex plane that is complex differentiable at every point in the domain. This means that at each point z in the domain, the limit f dash of z equal to limit h tends to 0 f of z plus h minus f of z divided by h exists. Properties. Analytic functions have a well-defined derivative. They can be represented by a power series expansions. Conformal mapping. A conformal mapping is a transformation of the complex plane that preserves angles locally. In other words, if two curves intersect at a point in the original place, their images under the conformal mapping will intersect at the corresponding point in the transformed plane. Properties. Conformal mapping are typically realized by analytic functions which are complex differentiable and satisfy the Cauchy-Riemann equation. Riemann mapping theorem. Riemann mapping theorem is: any simply connected region in the complex plane other than the whole plane itself can be formally mapped onto the unit disk in the complex plane. Implications and applications. Cartography. The Riemann mapping theorem has implications in cartography as it guarantees the existence of conformal mappings between various geographic regions and the unit disk. Examples of conformal mapping. First one is a linear transformation. Transformation W equal to Z plus A, where A is complex constant. Next one, scaling. W equal to AZ, where A is complex constant. This scales that the plane by a factor of modulus A and rotates it by the argument of A. Rotation. W equal to e power I theta into Z, where theta is the angle rotation. Fractional linear transformation. W equal to AZ plus B divided by CZ plus D. Exponential function. W equal to e power Z is the exponential function. Next, inversion. W equal to 1 by Z is the inversion. Applications of conformal mapping. Conformal mapping plays a crucial role in complex analysis. Solving boundary value problems. Conformal mapping allows for the transformation of complex boundary value problems in one domain to simpler problems in another domain. Mapping complex geometries. Conformal mappings can be used to map complex geometries such as polygons, circles, and regions with irregular boundaries. Fluid dynamics. Conformal mapping is widely used in fluid dynamics to study the flow of the fluids around obstacles or through the irregular channels. Heat conduction. Conformal mapping techniques are applied to analyze heat conduction in complex geometries. Mathematical physics. Conformal mapping techniques are widely employed in mathematical physics to study diverse phenomena. Conformal mapping and fluid dynamics. Conformal mapping plays a significant role in fluid dynamics, particularly in analyzing and understanding the behavior of fluid flow around obstacles or through the complex geometries. Flow visualization, potential flow theory, aerodynamics, hydrodynamics, boundary layer analysis, fluid structure interaction, numerical simulation. In summary, conformal mapping serves as a valuable tool in fluid dynamics. Conformal mapping in electrostatics. Conformal mapping is extensively used in in the field of electrostatics to analyze the behavior of electric fields and potential in complex geometry. First one is mapping complex geometrics. Second one is boundary value problems. Third, charge distribution, parallel plate capacitors, electrostatic force and energy, boundary element methods. Thank you.